Hello everyone, I am Chandrika and I am going to present HoloLens to sensor streaming application and user identification. First, I will explain my motivation behind the work, then I will talk about the problem. After that, I will talk about a related work last gesture. Then I will discuss the system design of HoloAuth. After that, I will show some results and analysis. Then I will discuss the conclusion and some future direction. And the end, I will be showing the demo of sensor streaming application. Most of the AR/VR devices use password or PIN for authentication. However, to do so, a user has to interact with virtual keyboard. Um, to input strong passwords using virtual keyboard can be difficult because of its latency issues, and therefore users choose weaker passwords most of the times. Many of the AirView applications are designed to be used in shared environment, and as the passwords are not strong, and an attacker can easily detect them. Therefore, this AirView authentication system is prone to shoulder surfing attacks. Multiple SOKs suggest that physical biometrics authentication can achieve better usability in case of AR/VR domain. However, not many of them are deployed because of the authentication time and accuracy issues. Variety of sensors are deployed in AR and VR to detect users' movement correctly. This way, the AR/VR systems can create better immersion for the user in the environment. One of such popular AR/MR device is HoloLens 2, which is developed by Microsoft. For in this project, I wanted to analyze if HoloLens 2 sensors data can be utilized to uniquely identify a person based on just their head movement. For that, I developed a HoloLens 2 sensor streaming application that can capture and stream data from multiple sensors. Also, after capturing data, I explored how a user's head movement can be utilized to uniquely identify a user. To do so, I had to collect data from multiple users. For this work, I collected data from 3 different users, 2 sets from 2 different users, and 1 set from another user. Each set has 3 to 4 repetitions of each gesture. Those gestures are simple and easy to do. None of the gesture takes more than 5 seconds, and these gestures were circle, triangle, square, W. After that, some training and classification is done, which I will explain in the later slides. The Glass gesture paper proposes an authentication system for Google Glass, which is based on security questions and user head movement. In this work, HoloAuth, I have used some methodologies which are proposed in Glass gesture. The HoloAuth system has 3 different sections. First is data collection, which is done by the HoloLens to sensor streaming application. The head gesture recognition portion, we use DTW or dynamic time warping algorithm to determine similarity score between 2 head gestures. Affinity propagation algorithm is used to find appropriate number of clusters, and then the cluster centers are enrolled as exemplars. From the head tracking data, multiple statistical features are extracted, and then a SVM model is trained using new data, then the performance of the SVM model is evaluated. For the data collector part, I implemented a Unity application for HoloLens 2 that can access data from IMU sensors, which are research mode sensors, and these are accelerometer, gyroscope, and magnetometer. It can also capture head tracking and eye tracking information from user. It can stream data over TCP to a server. This server is implemented in Python and it can run in the laptop. A detailed demonstration of this app is at the end of the slide. To uniquely identify a user based on their head movement, I utilize the gyroscope data, which is the rotational movement data, and also the head origin data, which is the position of head during any head movement. This data are separately used to train two separate SVM models, and later the performance of those models were compared with each other. This is a short demo of the HoloLens to sensor streaming application. Detailed demo is at the end. For head gesture recognition, first dynamic time warping algorithm is used to find out similarity score between two head gestures. The similarity score is the Euclidean distance between two aligned time series data. By comparing multiple head gestures, we can get a similarity matrix. Affinity propagation algorithm works on this similarity matrix to find out appropriate number of clusters. We do not need to provide number of clusters at the beginning, like k-means and k-medots for affinity propagation algorithm, and it uses a message passing concept between data points. Gyroscope data and head origin data, both of them has x, y, z value based on 3 axes. For each gesture on each axis, 23 different statistical features were extracted. The feature set is shown in the right side of this slide. So total 69 features were extracted per gesture, and a SVM model was trained. This is a popular choice for many biometric-based authentication. Also, grid search has been applied to find appropriate parameters. RVF kernel is used with 5-fold cross-validation. The output level is either the cluster identifier, that is the assigned cluster by affinity propagation algorithm, or the user identifier. Now I will show some results and analysis. Here the user was instructed to do a circular head movement. This slide shows the different signals captured by different sensors in HoloLens 2. At the left at top, the first signal is from accelerometer, which is the linear acceleration. Then the gyroscope detects the rotational movement. And then the third is the magnetometer data. At the right side at top, there is this head origin data, and the bottom is the eye cursor data. We can see that the eye cursor data is following the head. However, there is more data point in case of head, therefore it is smoother, and eye cursor data is jumpy. Now here we discuss how affinity propagation algorithm does clustering. In this slide, we use data from a particular user. In the left, in the true label, we see the instructions that were given to user. So the user was instructed to perform circular head gesture, triangular head gesture, and W and square. After running the affinity propagation algorithm over this data set, we see that the data was divided into 3 clusters. Circle formed a different cluster, triangle formed another cluster, and W formed another cluster. However, squares did not form another different cluster. These were assigned to the triangles. This can happen. It depends on how user moves his head. For this user, the square head movement was similar to the triangular head movement. And this is one of the reasons that the manual labeling was not chosen and affinity propagation was used to label the data. This way, we can get more information from a particular head gesture. Another dataset was captured from the same user in a different day. And this is the dataset in the right side, which was tested against the clustering in the left. We still see that the triangles are recognized as triangle, Ws are recognized as W, and clusters and circles are recognized as circle. Also, the squares are still recognized as triangle. From here, we can see that even if these two data were captured in different day from the same user, still there is a similarity. And we can see this similarity in the next slide a little more. Here, the one user was instructed to perform multiple circular head movements. And For these four head movements, we can see that the pattern in x-axis, y-axis, and z-axis, um, all the signals have followed particular pattern, and there is a similarity between these signals. So from this, we can see that a user, when they perform a particular head movement, there are some similarities. Here, user 1 and 2 were instructed to perform circular head movement and triangular head movement. At the top, the three figures shows the circular head movement. Here, we see that the signal from user 1 and user 2, they do not match for X, Y, Z. And this is true for triangular head movement as well. From this, we can see that even if the gesture is same, the user 1 and user 2 head movement are different. Also, a very clear observation from this slide is user 1 completes the head gesture before user 2. Now I will discuss the accuracy of the classification accuracy. First, the gyroscope-based trained SVM model can correctly identify the cluster ID 94% of the time, and it can also identify a user correctly 94% of the time. The head origin-based trained SVM model can determine the correct cluster ID 78% of the time. Also, it can determine the correct user 89% of the time. So it can perform better while identifying user. So we can see that the rotational head movement is much more consistent than the head position change while user moves his head. From these results, we can see that alone gyroscope data can be enough to uniquely identify a person. However, a broad user study is required to confirm the accuracy. It would be nice to explore the association of eye tracking data with head tracking data to improve the authentication system. It will be also interesting to check if an attacker can evade this type of authentication system, and if yes, what type of defense mechanism can be built. Now I will show the detailed demonstration of sensor streaming application. Hi everyone, as you can see, I have opened my TCP server in the laptop. You can see it in this monitor. It is running on a particular IPN port, and the HoloLens 2 app is configured in a way that it can communicate with the server. Whenever the HoloLens 2 application will be transmitting the data, the server will be able to capture them and store them in a text file with particular timestamp, so can be used for analysis later. For example, here I have previously captured some data, so I have all the information, but right now I will capture some new data which will be stored here. We can see later in the video. As you can see that I've already started the server. It is waiting for new connection request, so I will go ahead and open the HoloLens 2 app. Here you can see a bunch of digits, so right now I'm going to focus on the IMU section. The IMU data is basically the data from accelerometer, gyroscope, and magnetometer. All these sensors are research mode sensors and not directly accessible by public apps. These are all restricted capabilities. Right now, if I want to select any particular data, like for example I want to select data from accelerometer, I can click this button and it will only capture those. Right now, if the server was or the HoloLens 2 was streaming the data, it would be only transmitting the accelerometer data. I have also configured my voice commands, so if I say log gyroscope, it will only show the data from gyroscope, and during transmission it will only transmit the gyroscope data, and same goes for the magnetometer. But right now for the first experiment, I want to transmit the whole IMU section. If I click on the collector server, it will start transmitting, and you will be able to see that in the terminal the server is capturing data. I will show all the text files later in the video. So first let me start the server. So as you can see that server has started capturing the IMU data. If I say log magnetometer, so right now you can see that amount of data the server is capturing for each event is smaller. It's only capturing the magnetometer data. I will also get back to it later. Same I can do it with the gyroscope. So this was the development for part A, but you can see in the section there are two more sections here. One is head tracking and another is eye tracking section. So I will first stop the server, and in case of head tracking, I am showing the data of head origin, the direction, and head velocity and movement direction. So if I say log head tracking, it will only show us the data from head tracking, and similarly, if right now HoloLens 2 is transmitting the data, it will only transmit the head tracking data. You can see a point on the screen, orange point, that's actually the eye cursor. So I have configured this app to be able to capture eye gaze input. So it shows the eye origin, so from where the eye gaze is generated, the direction exactly where I am looking at, and the cursor basically a point on that particular direction in a particular distance. So the eye gaze cursor basically follows my eyes wherever my eye is moving. So if I say log eye tracking, yeah, so you can see that the data is visible in the eye tracking section. And now right now I will start the server again, and see the terminal is again capturing the data from eye tracking section. And same for the head, which I can control from here. And right now the terminal is capturing the data from head. So what if I want to capture data from all the sensors? So I'll say log sensors. So right now, if you can see, the terminal is capturing much more data for each event. So it is capturing data from all the sensors. So yes, this was the development for my part A and part B. I will now stop the server, close the app, and I will show you the text files that were captured by the server. So if I reload from disk, the first text file shows that I first transmitted the data, IMU data, so we can see those, and then we will only see magnetometer data, and in the final I'll see the gyroscope data. Later we only transmitted the eye data, then we transmitted the head data, and then we can see that the whole data for eye tracking, head tracking, and IMU sensors I'm able to capture. This captured data, I use it for my part C for analysis, that if we can uniquely identify a person based on their head movement. So thank you for watching this. Thank you everyone for listening to my presentation.